everyone. Hopefully you are all staying safe and healthy at home. Thank you for attending my talk about using stable isotopes to determine the effect of diet on the preferential food use in the yellow-rumped warbler. This research was completed as part of an undergraduate research thesis at the University of Western Ontario with help from the Advanced Facility for Avian Research. This intricate map of lines is actually only a portion of all the metabolic processes that occur within the body. So, it goes without saying, metabolism is complicated. This complicated flow can be altered by diet, time of day or year, or even temperature, shunting certain nutrients out of one path and into another. The flexibility of those metabolic pathways is well known to endurance athletes who may regularly practice carbohydrate loading before runs. This involves eating a high carbohydrate diet beforehand to increase stores of glycogen in the muscle, thereby increasing the body's capacity for endurance exercise. However, migratory birds are arguably some of the best endurance athletes on Earth. What's their secret? Before leaving, birds are perfectly poised to quickly put on mass amounts of fat on a high carbohydrate diet. Fat is a primary fuel source for migratory birds, but it can only get them so far. Protein will also be heavily utilized during their journey. Metabolizing protein provides water, gluconeogenic precursors, and may also lighten the bird's load during flight. But this creates yet a new problem. Protein, unlike fat, cannot be stored in the body. Catabolizing protein means eating your own muscle tissues and organs, and relying too much on endogenous protein results in death. For migratory birds, protein is the limiting factor. Could they alter their metabolism through diet, like human athletes, to rely less on or store up on protein before leaving? Previous research has shown that frugivorous birds did have a greater reliance on fat during migration, whereas insectivorous birds relied greater on protein. Given this information, we hypothesize that within a species, omnivorous birds could alter their nutrient oxidation by altering their diet composition. Those who eat a high protein diet before migration might use more protein as fuel in the form of amino acids, whereas those who eat a high carbohydrate diet before migration might use more carbohydrates as fuel in the form of glucose. This means that birds could be forced to have different migratory patterns depending on the season. Long bouts in fall when berries are around, but many short bouts in the spring when insects are flourishing. The yellow-rumped warbler was chosen as our model organism as it is a prolific omnivore. It is able to thrive on a totally fruit or insect-based diet and is a short-distance migrant with potentially more flexible migratory patterns, thereby making it the ideal species to ask this question. A paper previously done by my supervisor analyzed plasma metabolites in yellow-rumped warblers to see how diet composition could alter nutrient oxidation. Birds were fed a high protein or high carbohydrate diet and were flown in AFAR's wind tunnel, and plasma metabolites were measured in the blood. Interestingly, this study found that nutrient composition had no effect on plasma metabolites in yellow-rumped warblers while in flight. However, plasma metabolites represent the concentration of the byproducts of nutrient breakdown in the blood and therefore do not accurately represent actual nutrient flux. Measuring stable isotopes in the breath using artificial enrichment has been done in the past to more accurately represent the flow of nutrients. Enriched tracers, which are nutrients labeled with heavy carbon, are administered to our yellow-rumped warblers and are broken down. The labeled macronutrients appear in the breath at their oxidative endpoint, CO2, allowing us to find our labeled carbon once more. The nature of how the heavy carbon shows up in the breath can tell you a lot about how the nutrient was metabolized. For example, depending on the type of enriched tracer administered and how it is administered, patterns of oxidation will be different. In house sparrows, you can see that a greater amount of leucine was oxidized than glucose. Note differences in scales on the y-axes between the two graphs. In addition, when glucose was given dissolved in water rather than oil, it reached peak oxidation rate quicker. For our experiment, we used glucose to represent carbohydrate oxidation and leucine to represent protein oxidation. Here's the setup that we used to perform breath testing. On the far left side of the screen, you can see the computer monitor, which is showing real-time values of 13CO2. The large machine under it is a mass spectrometer, which measures the CO2 in the breath. This arrow points to the chamber where the bird will be placed. This chamber is airtight and is constantly flushed with CO2-free air, so the only CO2 measured will be what the bird produces. Because this experiment used a new mass spectrometer that measured values in real time, the entire experiment was done in 2 steps. First, a methods development step, and then diet manipulations were performed. On this slide, you can see a table of what the diets contained. The high carbohydrate and high protein diet had approximately opposite ratios of carbohydrates to protein, as seen on the bottom of the table. On the right, pictured are images of diets in the bowls that were given to the birds. The methods development part of the study proceeded using the following experimental design. 10 birds were split into 2 groups of 5. Birds were fasted for 2 hours before any breath was measured. 1 minute of baseline levels of 13C in the breath were collected. Then birds were placed in a QMR machine to get values of fat and lean mass. Birds received either 10 milligrams of 13C glucose or 2 milligrams of 13C leucine by gavage, and then were placed in the mass spectrometer for 2 or 4 hours respectively. Differences between procedures for leucine and glucose were due to the different solubility of leucine in water, and as birds given leucine came back down to baseline levels of 13C within 2 hours. When given via gavage, a syringe as shown here is used to administer the enriched tracer directly into the bird's crop. A week later, the birds received the same tracer that they had been given before, but this time by subcutaneous injection, and the same procedure was used to collect breath. From our methods development, we found that the route of administration had a large influence on the maximum oxidation rate, regardless of the tracer. Throughout this presentation, red dots will represent mean values and gray dots represent individual values. The top 2 graphs present the maximum oxidation rate reached by the tracer within the time frame it was given, and the bottom graphs represent the time this maximum oxidation rate was reached. On the left-hand side is values for birds given leucine, and on the right-hand side presents birds given glucose. From this, we can see that tracers given via gavage reached higher maximum oxidation rates at a much lower delay than those given by subcutaneous injection. This finding comes at no surprise. Previous research has shown that orally dosed tracers tend to be metabolized quicker and reach higher rates. Nutrients tend to be oxidized quicker by the digestive organs, and therefore giving them to the digestive organs orally fast-tracks their metabolism. To model cumulative oxidation, we used a Gompertz growth equation. This equation is defined by 3 constants, A, B, and K. A represents the value of maximum oxidation, B represents the delay at which the maximum slope was reached, and K represents the steepness of the curve. When comparing percent dose oxidized, we can see that the final cumulative oxidation did not differ between routes of administration, but the timing of maximum slope and the steepness of the slope did change. These graphs present percent dose oxidized for each enriched tracer over time. When given via gavage, the data is presented with a blue line, and when given via injection, it is represented by a yellow line. When given via gavage, the maximum slope was reached with less of a delay, and the slope was steeper, and there were no differences in the value of final cumulative oxidation. This lets us proceed to the diet manipulations part of the experiment with confidence. For the methods development part of our experiment, we began altering diets. For this part of the experiment, 20 birds were split into 2 groups of 10 and given a high carbohydrate or high protein diet for at least a week before any testing occurred. Each diet received both tracers by subcutaneous injection and underwent the same protocol that was used in methods development for collecting breath. However, breath was collected for just 2 hours, as this was a sufficient amount of time for both tracers to reach their maximum oxidation rate values. When pooling values across both diets, maximum oxidation rate differed depending on the tracer administered. Leucine, on the right-hand side of both graphs, had a slightly higher maximum oxidation rate and with a slightly shorter delay than did glucose given by the same method. For cumulative oxidation, A, B, and K also differed between tracers when pooling values for diet. Values for A are seen in the first graph, displaying final cumulative oxidation. Values for B are seen in the second graph, displaying the delay and maximum slope. And values for K are seen in the last graph, displaying the time constant. We can see that more leucine was oxidized and had a steeper slope and with less of a delay in maximum slope than glucose, regardless of diet. However, diet did not influence tracer oxidation rates. The top 2 graphs display the maximum oxidation rate, and the bottom 2 display the time of maximum oxidation rate. On the left-hand side are birds given leucine, and on the right-hand side are birds given glucose. You can see that within a tracer, diet did not influence the timing or value of maximum oxidation rate. Cumulative oxidation only differed between diets in the values of maximum slope delay and the steepness of the slope. Presented here is the percent dose oxidized for each tracer compared between diets. The graph on the left presents values for birds injected with leucine, and the graph on the right presents birds injected with glucose. Birds on a high carbohydrate diet are represented with the green line, and birds on a high protein diet are represented with the purple line. This data shows that birds injected with leucine had slightly lower delays in maximum slope and a slightly steeper curve when given a high carbohydrate diet. However, there were no differences in the values of A, B, and K for birds given glucose. What can we take from these results? While the data did support the hypothesis that diet could alter nutrient oxidation, the results were opposite to the predictions. Instead of birds fed a high carbohydrate diet utilizing more carbohydrates, they used the leucine tracer more efficiently. The reason for this may be due to a concomitant increase in fat catabolism on a high carbohydrate diet. Leucine is a ketogenic amino acid, and therefore if pathways for metabolizing fat are upregulated on a high carbohydrate diet, it is possible that leucine is getting preferentially used over raw carbohydrates, which first get turned into fat before being metabolized for energy. Secondly, this could be an adaptive response by the warblers to increase ketone body creation when eating a protein-poor diet. The birds could be so-called ketone body loading to increase their capacity for endurance exercise. Since protein is the limiting factor, having ketone bodies in stores could spare body protein. In the future, we could learn much more about how nutrient oxidation may be altered by diet by using different amino acids. I suspect the results we found were highly dependent on the possible fates that leucine has in the body. In addition, it is possible that diet may only change metabolism while in flight or undergoing regular heavy exercise. Finally, long-distance migrants, or birds that migrate over large bodies of water, may be under greater evolutionary pressure to become super efficient migrators, and therefore may exhibit more metabolic flexibility than short-distance migrants. Thank you for listening to my presentation. I'd also like to thank all the wonderful people that helped me complete this research. Have a wonderful day.